All right, folks, it's Bass Action back in action here. In this video, we're going to do a quick overview of what exactly it means for something to be a conic section, and we're going to do a quick compare and contrast of what we will call the standard forms of each of our conic equations. So the first thing I want to call your attention to is up here at the top in these images here that I have pulled from your textbook right here. And this is actually what it means for something to be a conic section. A section means that it's going to be a cross section of the intersection of two different geometric figures. So what we can look at here is on, let's say, our circle. We've got two cones that are joined at their vertex. We have a nice line here crossing through. You can think of it as the height of both of these conics that's going to go straight through. And then I've got a plane, and as the plane crosses through just one of the cones, as it crosses through, if that plane is level, its cross section, what we're going to get, the intersection of the two, is a circle. Now, if we tip that plane just slightly, we're going to get what's called an ellipse. And now it's not going to look like a nice perfect circle, it's going to actually look like it's stretched out. If the plane gets tipped enough that it actually exits, let's say, through the top here of the cone, or if we had it down here the bottom, now what we're going to get is our parabola. So it's no longer going to be complete. And then if we can orient the plane so that it crosses through both cones simultaneously, we will have a parabola. What it looks like here is a parabola on the top and on the bottom, and we're going to call that a hyperbola. Now, don't worry too much about these actual intersections here. I'd just like you to see where they came from, because we are not going to work with these geometric figures. We are going to look at this purely from an algebraic perspective. So what we want to understand are the equations. Now, the first two that I'm going to have us take a look at here is the circle and the ellipse, because the circle and the ellipse are connected, okay? This circle is really a special case of an ellipse. Now, we've already studied circles, okay? We should already be familiar with this equation in that we've got our center. We already know that this is going to be our center. We already should be familiar with the fact that these two are squared, and we should be familiar with the fact that these are both a plus. Now, you'll notice that I highlighted here, but I don't have a sign there. There's an implied positive in the front of this, and it's important that you remember that there is an implied plus sign in the front. We also want to remember, and I've already written here, you can pause and write it down, that this right-hand side is the radius squared. So this equation here is in fact the equation for the circle that I've given you. We can see on this circle that my center is over 5 and up 2, and that matches my circle equation. We can see that the radius here of the circle that I've graphed for you is a 9, that this is I didn't mean to say 9, is a 7, and that is in fact going to be the radius squared there. Now, let's take a look at this ellipse down here. You'll notice that it looks a little bit more complicated because now I've got some fractions. I still have highlighted this front where there's nothing written there to remind you that there is an implied plus. What I want you to know is that these two signs have to always both be positive for our ellipse. Now, they both have to be positive because the ellipse is connected to our circle, and those are always both positive. An ellipse, however, because the amount that we're going to go left and right is going to differ than our up-down, we can see it here, left-right, and our up-down. On our circle, our left-right is the same as our up-down. On the ellipse, our left-right from the center is going to be different. So because of that, our equations are always going to equal 1, but these denominators are going to be different. So our left-right here, we can see on our graph, our left-right here from the center is a 6, and our up-down from our center is a 4. Now, these two numbers are in fact connected to these denominators. Just like on our circle, our right-hand side was our radius squared. On our ellipse, our denominators are going to be these distances squared. So our up-down distance was 4, our vertical distance was 4, and if I square that, I get 16. our right or left right or our horizontal distance was 6, and if I square that, I'm going to get a 36. Up here, we're now going to look at a new form of a parabola. We're going to have a new video for the parabolas, and you'll see that also in the playlist. If we look at our parabolas, what we're going to notice is that we're still going to have a vertex, but now we've got that's going to easily be identified. Okay, so our vertex here we can see is a 0, and now we're actually going to flip this sign of a -5. So I'm going to have a 0 and a -5, and we can see that point right here. On this parabola, I have a -4, and y, there's no value being added or subtracted, so it's 0. So we'll have a -4, 0, and that also connects right here. So -4, 0, and on this one we have a 0, -5. So we're now going to be able to easily read our vertexes. The main thing that you should notice here is that now all of a sudden we've got these left, right, this sideways opening parabolas, whereas before we only worked with ones that either opened up or potentially opened down. So we're going to have this new form that's going to open left, right, and we're going to want to be able to easily tell the difference between these two forms. So what I want to call your attention to is when I look at this left, right parabola, it either opens to the right or it might open to the left. What I want you to notice is that this parabola is crossing this y-axis twice. Now, remember, we could slide this parabola over and it might not cross the y-axis at all, but what we want to think about is the potential of crossing. So as we see this cross this y-axis twice, we're going to notice that in the equation, it's the y-axis that gets squared. So whichever axis it might cross twice is the variable that should be squared in the equation. And up here are good old up-down ones that make sense. It's crossing the x-axis twice or has the potential to cross it twice, and it's the x value that's going to be squared. I also want you to notice these coefficients. The exponent and the coefficient will always have to be on opposite sides, and this coefficient is always going to have to be factored out of these expressions here. So we are going to practice getting these in the forms, but I want you to just make some notes and start to get that new form in your mind. The last one we're going to look at is that hyperbola. The important thing about the hyperbola is, again, we have this implied plus in the front, but now I want to call your attention to the fact that the signs are different. We now have a minus in the middle. So the leading sign is a plus. We don't have to write it. The sign in the middle will be a minus, and just like our ellipse, it is always going to equal 1. The actual parabola or hyperbola is only these bold branches, but we're going to draw in these dotted lines to help us create them, because it's going to create these asymptotes that our hyperbola is going to approach. This is also going to be very closely connected to our equation. We can see the distance to that point on the branch, that horizontal distance from our center is going to be 2, and that horizontal distance, you can see if we square it, is that denominator. Our vertical distance here is going to be a 3, or I meant to say a 5, struggling here today. And that distance, if I square it here, is going to be our value underneath our y. Now we're going to do lots of practice with these videos or with these equations, and so you'll get really, really familiar. But these are just little details that I want you to start thinking about before we get into writing them in the form on your own.